Hello everyone, this is part 1 video on past year NEET questions from the chapter hydrogen. Now in terms of weightage, this may not be that important a chapter, but in terms of scoring, because we do get pretty much straight questions and theory based questions from this topic. So in terms of scoring, when we get questions from this chapter, they will be very easy to score. We'll start with a question that has come in the NEET 2019. The method used to remove temporary hardness of water is. So they have given 4 options. Option A is synthetic resins method. Option B is Calgon's method. It is the short form for calcium gon. Option C is Klux method. Option D is ion exchange method. Now synthetic resins method, it is basically a method where we will exchange cations and anions in succession by using the synthetic resins, which will be a little bit more effective than the regular resins. So this is not a method to remove temporary hardness of water. This is a method to remove the permanent hardness of water. Now just to bring to your notice, temporary hardness of water is because of the presence of calcium and magnesium bicarbonates. Permanent hardness will be because of the presence of calcium and magnesium chlorides and sulfates. Calgon's method is another method that is used to remove the permanent hardness of water, where we will be using sodium hexa metaphosphate. So that is the Calgon's method. Klux method, this is the method that is used to remove the temporary hardness of water along with simple boiling. So boiling also can remove the temporary hardness of water. So what happens when we boil is the bicarbonates will dissociate to produce the carbonates, and carbonates of the calcium and magnesium are insoluble. So what would happen is they will form a precipitate. So boiling and Klux method are the 2 methods that are used to remove the temporary hardness of water. Option D, ion exchange method, it's also called as the permutate method, where we will be using zeolites. So this is a method again for the removal of permanent hardness of water. Now what is this Klux method? So Klux method calculated or measured amount of lime water. So lime water is when we add quick lime to water, we will get calcium hydroxide in solution with water. It is called as lime water. Calculated amount of lime water will be added to the water containing the temporary hardness. Temporary hardness will be having calcium and magnesium bicarbonates. So what would happen is the insoluble precipitates of calcium carbonate, or in the case of the magnesium bicarbonate, we will have magnesium hydroxide also getting formed. So this way the lime water is able to remove the calcium and magnesium ions from the water. So this is the Klux method. So the 2 methods that are used for the removal of temporary hardness of water are Klux method and then boiling. The other methods that have been described over here, the synthetic resins method or the natural resins method, Calgon's method where we use sodium hexametaphosphate, or the ion exchange method, which is also called as the permutate process where we use zeolites, all of them are used for the removal of permanent hardness of water. So the correct answer for this is option C, which is the Klux method. Moving on to the next question, this is the question that has come in NEET 2019 Odisha paper. The number of hydrogen bonded water molecules associated with CuSO4.5H2O. This is called as blue vitriol, and it might be worth remembering that these vitriols, blue vitriol and green vitriol, is FeSO4 7H2O. In some of the not in the NEET or AIPMT, but in some other competitive examinations, they have even asked straight questions on identifying what is the compound that corresponds to a particular vitriol. So copper sulfate .5H2O is also called as blue vitriol. We need to find how many number of water molecules are hydrogen bonded. So if you look at the copper sulfate dot 5H2O, it is a coordination complex, and the structure of the coordination complex will be represented like this. Within the parenthesis we have CuH2O 4 times, which means the 4 water molecules are bonded to the copper ions through coordination bond, and the water molecule which is outside the coordination sphere is basically the one that is hydrogen bonded to the sulfate ions. So only one water molecule is hydrogen bonded, the other 4 water molecules are bonded to the copper ions through coordination bond. So the correct answer for this is option B, which is one water molecule. Moving on to the next question. This is the question that has come in the mains paper 2010, because back then we used to have the prelims and mains format for AAPMT. Some statements about heavy water are given below. So the first statement is heavy water is used as a moderator in nuclear reactors. Second statement is heavy water is more associated than ordinary water. More associated would mean the molecules are more bonded to each other, more intermolecular forces. Generally, when a liquid is more associated, then the boiling point of the liquid must be higher, because it will be difficult to move the particles of the substance from liquid state to vapor state. Third statement is heavy water is more effective solvent than ordinary water, and we know water is actually a polar solvent. So if we say that heavy water is more effective solvent, then heavy water must be having high polarity. So we look at the question, which of the above statements are correct. So we need to identify which of the statements given in these three are basically correct. Now the first statement, which is heavy water is used as a moderator in nuclear reactors, is correct. In fact, that is the application of the heavy water. It will be able to slow down the fast moving neutrons, because fast moving neutrons, they will not be able to induce the nuclear fission reaction. So they will be slowed down by the use of moderators, and heavy water is one of the substance that is used as moderator in the nuclear reactors. The second point is about heavy water being more associated than ordinary water. Now for this, when we look at the boiling point comparison, the ordinary water at 1 atm external pressure will boil at 100 degrees centigrade, whereas the heavy water boiling point will be 101.42, which means the boiling point of heavy water is higher. That would mean that the heavy water must have stronger intermolecular forces, or heavy water must be more associated than the ordinary water. So the option 1 is correct and 2 is also correct. Now coming to the third one, heavy water is more effective solvent than ordinary water. Now how polar a solvent is decided by the dielectric constant. So in physics, you will be able to understand what is the exact meaning of this dielectric constant. So from chemistry perspective, more polar a solvent is, the dielectric constant of the solvent will be higher. So if you look at the data for both water and heavy water, for water the dielectric constant value is 82, and for heavy water it is only 80.5, which would mean that water, the ordinary water, is more polar, and hence it will be able to act as more effective polar solvent than the heavy water. So the third point given over here is not correct. So the correct answer for this question is option A, which is both 1 and 2 are correct. So heavy water is used as a moderator in nuclear reactors, and heavy water is also more associated than the ordinary water, which we can see from the boiling point data. But between heavy water and ordinary water will be able to act as more effective polar solvent. Moving on to the next question. This is a question that has come in 2003. The structure of H2O2. So as we can see, quite a number of questions would come from this hydrogen peroxide related areas. The structure of H2O2 is, the options given are spherical, non-planar, planar and linear. So if you look at the structure of H2O2 as such, it is a non-planar structure, but there will be some variation in terms of the bond angles when we look at the gaseous state and the solid state. We can see if we take both these oxygen atoms to be the line, one hydrogen atom will be in one plane, other hydrogen will be in the other plane. That is why we call the structure as a non-planar. And the angle between the two planes, we can see in the gaseous state it is 111.5 degrees, which is reduced to 90.2 degrees in the solid state. This angle is basically called as the dihedral angle. So the reason why the dihedral angle reduces in solid state is because of the hydrogen bonding. So hydrogen bonding is the reason why the dihedral angle will be reduced from 111.5 degrees to 90.2 when we look at the structures between the gaseous state and the solid state. Another bond angle that is over here is the OOH bond angle. So in the gaseous state the value of this is 94.8, and in the solid state the value of this will be 101.9. So this is about the structure of H2O2, and of course the structure is a non-planar structure. So the correct option for this is option B, which is non-planar. We'll move on to the next question. This is the question that has come in 1998. Which one of the following pairs of substances on reaction will not evolve hydrogen gas? Now copper being less reactive than hydrogen in terms of the reactivity series, it will not be able to displace hydrogen from its compound. So copper, when it is reacting with aqueous HCl, it will not be able to evolve hydrogen gas, whereas the other options mentioned over here, starting from iron with steam. So iron, when it is reacting with steam, iron reacts with steam. It will not react with hot water or even cold water. More reactive metals like sodium, potassium, they will react with even cold water. Mildly reactive metals like zinc, they will react with hot water, zinc, magnesium, and little bit less reactive metals like iron, they will be able to react with steam. So iron with steam, it will be able to form iron oxide and then evolve hydrogen gas. Iron with aqueous H2SO4, because iron is placed above hydrogen in the reactivity series, it will be able to evolve hydrogen gas. And ethyl alcohol, when it is reacting with sodium, it will form sodium ethoxide, and again the hydrogen gas will be evolved. So the only option which will not evolve the hydrogen gas is option A, which is copper and HCl aqueous solution, because copper is less reactive than the hydrogen in terms of the reactivity series. Moving on to the next question. This model of question has come in both 97 and 96. This is the only numerical area in the hydrogen chapter, which is about the volume strength of the hydrogen peroxide solution. The question is, what is the volume strength of 1.5 normal H2O2 solution? Now first we need to understand what is the meaning of this volume strength. If you look at H2O2, it will dissociate even in the presence of mild contaminants or dust, or even in the presence of light, to produce oxygen gas. So the dissociation of H2O2 will be able to produce oxygen gas. Now H2O2 is a liquid. If you take 1 liter of H2O2 liquid, how many liters of oxygen gas at STP will be produced by the dissociation of 1 liter of the H2O2 solution? That is what we will call as the volume strength. So volume strength is basically how many liters of oxygen gas at STP will be evolved when 1 liter of the H2O2 solution is dissociated. So what we'll do is, when we look at the given H2O2 solution, it is a 1.5 normal H2O2 solution. So we can find the strength of H2O2 solution in terms of mass. So if you multiply normality with the equivalent weight, this will give us what is the mass of H2O2 present in 1 liter solution, because normality is the number of equivalents present in 1 liter multiplied by the equivalent weight of H2O2. So H2O2 molar mass will be 34 grams divided by 2. the total charge on hydrogens here is there are 2 hydrogens, 2 into 1 will be 2, so we divide by 2, we'll get it as 17 grams. The equivalent weight of hydrogen peroxide is 17 grams. So when we multiply normality with the equivalent weight, we will be able to find out in 1 liter of the given H2O2 solution what is the mass in grams of H2O2 present. So we can see here, if we multiply the normality 1.5 with the equivalent weight of H2O2 17, we will get the mass of H2O2 present in the 1 liter to be 25.5 grams. And when we look at the dissociation equation, 2 moles of H2O2, which will be 2 into 34, 68 grams, will produce 1 mole of oxygen gas, and at STP conditions the volume of 1 mole oxygen gas will be 22.4 liters. So if 68 grams on dissociation can give us 22.4 liters, what we have in 1 liter solution is 25.5 grams. This would give how much? Let us say it is X. So it will be in proportion X by 22.4 will be equal to 25.5 divided by 68. So X will be equal to 25.5 divided by 68 into 22.4. So what we can see over here is this will give as an answer close to 8.4. So the volume of oxygen gas at STP that is liberated from 1 liter of the H2O2 solution is 8.4 liters. So the correct answer is option B. Now we have a ready-made formula also for this, if we can remember, because a 1 normal solution would mean it contains 17 grams in 1 liter, because equivalent weight is 17 grams. 68 grams from the above calculation will give us 22.4 liters. So the 1 normal, which contains 17 grams, the volume of O2 that can be released is 17 by 68 into 22.4, which is equal to 5.6 liters. So this is the volume strength of 1 normal. Now volume strength of any solution will be equal to normality into 5.6. We can check even in this question, normality is 1.5, multiply by 5.6, we'll get the answer to be 8.4. If they talk in terms of molarity, then since for H2O2 the valency factor is 2, the volume strength will be molarity into 11.2, so it will be just double. So these are the 2 shortcut formulas that we can remember to find out the volume strength of hydrogen peroxide solution. So when they give us the normality, it will be simply normality into 5.6. When they give us the molarity, it will be molarity into 11.2. This is another question that has come on the structure of H2O2. The OOH bond angle. Now this is not the dihedral angle, they are asking about the OOH bond angle in H2O2. Now as we have already seen, the gaseous state and solid state, the bond angles will be different. The OOH bond angle over here in the gaseous state is 94.8 and in the solid state it is 101.9. So the average of these two will be coming close to around 97. That will be the OOH bond angle in the case of H2O2. So the correct answer for this is option D, which is 97. Moving on to the next question. This is a question that has come in 1994. Which of the following groups of ions makes water hard? Now, as we already seen, the hardness of water will be because of calcium and magnesium ions. If you have bicarbonates, then that will be the temporary hardness. If you have chlorides and sulfates, then that will be the permanent hardness. So here it is not because of sodium and bicarbonate, it is not because of potassium and sulfate, it is not because of ammonium and chloride, it is because of magnesium and chloride. So the correct answer for this is option B, which is magnesium and chloride ions. Move on to the next question. This is a question that has come in 1993. One would expect proton to have a very large. A proton is basically the hydrogen atom, because in a hydrogen atom, protium is the only isotope which will have one proton inside the nucleus and one electron. Once this electron is released, the H plus basically contains a single proton. It has got only unit positive charge, so definitely it will not have a large charge, and there is no concept of talking about ionization potential for this because it doesn't have any electrons. And radius, since it is only one proton, the radius is also very small. What would be the property of the proton is, it has got a unit positive charge, but the size is very, very less. Because the size is less, when we look at the charge density, because charge density is calculated as charge by volume. Here the volume is very less, so the charge density will be very, very high. Now for whichever ion the charge density is high, that when it is dissolved in water, it will be able to form many layers of water around it, and it will be able to have a higher level of hydration. So the hydration energy will be high for the proton. And I mean, just to understand how it will occur, so it can be surrounded by 4 water molecules to form H9O4 plus, we call it as Egan, and it can even be surrounded by just 2 water molecules, we call it as Jundel, and the hydration energy of proton will be higher. The correct answer is option C, which is the hydration energy. So we'll continue in the next part of this video.